Hi everyone. Okay, so today we will go on to the chapter 9, which is the discrete transform. So what is discrete transform? Okay, so as we mentioned before, your image can be represented as either in a spatial domain or it can be in a frequency domain. Spatial domain is pixel by pixel, as what we did before, where you can enhance the image, okay, by pixel, where you have the resolution, the number of pixel in one image. Okay, what you will do is you will manipulate the pixel value. So either you want to add, okay, to image means you will add the 2 pixel image, okay, with 2 images, okay, into one, add 2 image into one. So you will deal the process pixel by pixel, okay. But for now, it is in a transformation, frequency domain, okay. So how to get the frequency domain? You can either use this transformation formula, okay, or mathematical tools. So it can be either Walsh-Hadamard, okay, or Fourier or cosine and separable properties, okay. So transformation is a process of changing the representation of an image from one domain to another domain, okay. So the one domain is the spatial, and then you transform, you will get a frequency domain. So what you will do is to map data from spatial domain to frequency domain, okay, which sometimes we also call as spectral domain, where all the pixels in the input contribute to each value in the output, okay. So we already done the transformation, okay, but it is only a one-to-one mapping. So for example, you have one image, okay, by using different color model, then you want to change into another color model. For example, you have the RGB color model. Now you are going to transform into a grayscale color model, okay, grayscale color. So there is a process of transformation as well, but it is a one-to-one. But for the frequency domain, each of the pixel in your input will contribute to the output, okay. So how it will contribute? By using the transformation equation. So it means that it not only deals with the pixel value, so it will also take the characteristic of the image as well. For example, if your image is in a contrast image or a blur image, okay, low contrast image, so it will transform, okay, so that your output image also will take this characteristic, okay, the input characteristic. So this is an example, okay. So the left side is the spatial image, where it deals with pixel by pixel, where you can see, okay, what is the image all about. But if you transform into a frequency domain, it will be on the right side, okay, where you use the discrete Fourier, okay, transform, okay, the frequency domain, then you will have a different representation of the image. So you cannot see what is the image all about, okay. So it is used in image analysis and processing to provide information regarding the rate at each the gray level change within an image, okay. So this is where the spatial, frequency or sequential. So the left side is the spatial domain and the right side is the frequency domain, where the information is only on the rate of the gray level changes, okay. So different image will transform into different output of the spatial domain. So with this frequency domain, you can do all what you have done before, where you will do the enhancement, okay, you can reduce the noise, restoration, or you can do the compression, okay. So the difference is only the technique that they use and the input, okay. So as been learned before, if you have a spatial domain, so you will do the restoration where you will have the filtering technique, okay, either it is a mean filter or another type of filtering. But for the frequency domain, you still do the same thing, okay, from the frequency image. Okay, so it is not different, okay. The process will be the same as what you did in the spatial domain, but the only difference is the technique being used, okay. So for restoration, if you have a frequency domain, they will have their own technique, but the spatial will have their own technique. So here in frequency, you will deal the image with the frequency images. Okay, so next is the discrete transform. Discrete form of this transformation is obtained by sampling the continuous form of the function on which these transforms are based. So this we call it as a basis function. Okay, so these functions are typically sinusoidal and or rectangular. Okay, either it is you use the sine, cosine, okay, formula, or it can be a rectangular. Rectangular means your coefficient is only involve 1 and 0. Okay, only two different coefficient. But sine, it will have their own formula. Okay, the graph will be the same. So the discrete version of 1D basis version, we call it as a basis vector, and discrete version of 2D, we call it as basis images or basis matrix. Okay, so for 1D, we call it as a basis vector, so it can be either vertical or horizontal, okay. But for the 2D, you will have the matrix, okay. So the mathematical term of projecting the image into basis images is an inner product, okay. So inner product is where you have the basis image and the input image. So the process is what we have done before is like a convolution. Okay, convolution means you will have your input image and you will convolve the input image with the filter. Okay, so then you will remove the noise or you want to enhance the image. Okay, so this is the same. Okay, where you do the inner product means you will do the convolution, okay, from the basis image with the input image. That's how you will get the frequency domain. Okay, so this is basis vector versus basis image. Okay, where if you have a 1D sinusoid, so it is a graph, okay. But if you have a basis vector, it is a sample of 1D sinusoid. Okay, so a basis image is a sample, okay, sinusoid shown in 2D. So the brightness of each row correspond to 1D sinusoid, which are repeated along each column. Okay, So you can imagine. So here is light. So let's say you have one line here. Okay. Let's say you have one line here. Straight line. Okay. Then you transform into this graph. Okay. So for the left side is the white color. Okay. The bright color, and the right side is the black color. So this is what you will get. So again, basis vector is a 1D. The image is in the 2D. So the ways in which the image brightness level change in space define the spatial frequency. So for example, rapidly changing brightness correspond to high spatial frequency. Okay, slowly changing relate to low frequency. Okay, so it means that if the frequency is 0, so the gray level only 51. Okay, this is A, where the frequency is 0. So frequency 0 means there will be no changing. So it only have one color, which is gray. Okay, but for this one, the gray level is 51. But for the B, frequency is 0, means no changing color. Okay, but the gray level is 200. The color is 204, the pixel value. Okay, so if you have frequency 1, means there will be only one changes. Okay, from light to brighter. Okay, so C is in a sine wave. Sine wave where you will have like this. Okay, so that's why your image is a grayscale image where you will have changes, okay, from bright to darker. But for D is a horizontal square wave. Okay, means that you only have white and black. So that's why there will be only two color here. But if frequency is 20, 20 means you will have 20 changes. Okay, white, black, white, black. Okay, white 1, black 1, white 3, 4, 5. So until the end, so the total changes is 20. Okay, so again, this is the sine wave where you will have gradually changes from white to black. But for the F, still the same, the frequency is 20. Okay, where you start with 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the changes of white to black considered as one frequency. Another one frequency. So the total changes is 20. But this one is a square wave, means it is a white and black. This is white. This is black.